So you might remember the idea of a basis for a vector space, right? Let's remember some concepts. Say I want to create a basis for R3. R3. My vectors will all belong to R3. I want to create a basis for these vectors. How many vectors do I need? 3. I need 3 vectors. One example, we call the canonical basis. How is the canonical basis for R3? 1, 0, 0. This is one of the vectors. The second one is this. The third one is this. This is the canonical basis. There are other options. For sure, this 1, 2, 3, 3, 2, 5, 1, 0, 0. This might be a basis, right? Not orthogonal, not normalized, therefore not orthonormal. I can create another orthonormal basis, which is not the canonical basis. For instance, 0.6, 0.80, then minus 0.8, 0.6, 0, then 0, 0, 1. Not the canonical basis, but it's an orthogonal basis. If I do the inner product between any two of these 3 vectors, I get 0. And all of the 3 elements have unit norm. So all of these are options. I have infinite options of bases. Now we're going to treat periodic signals. For instance, say I have a signal x of t, which is periodic. Let's do a square wave. It repeats at every period t0. So we will treat periodic signals here exactly as if they were vectors. As if within one period, we have a vector with infinite entries because it's a continuous signal. When we treat discrete signals, the entries will be finite. Just like here we have 3 entries, we will have a finite number of entries for continuous periodic signals, but an infinite number of entries for a continuous, finite for discrete, infinite for continuous. So if I need 3 vectors here, how many vectors do you think I need to represent this, the basis for this space? The space of all continuous signals with a certain period, T0 or T0. How many vectors do I need? Here I have one vector which is 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1. But I can draw anything here in this interval, and I want a basis for the set of all functions that can be written here. If for R3, I need 3 vectors for my basis. For this R infinity, how many vectors do I need? An infinite number of vectors. So they are these guys. We've seen before that these guys are orthogonal, right? I created this script. There are 2 parameters. This wave is N1 has frequency N1 omega 0, and the second wave has frequency N2 omega 0. So this script shows us that for any N1, N2, which are different among them, the inner product is 0. So we demonstrated empirically that this basis is orthogonal, that this set of vectors is orthogonal. Now the news are, if I have the infinite group of vectors with frequency 0 times omega 0, 1 time omega 0, 2 times omega 0, 3 times omega 0. Actually, they're written here. E to the j 0 omega 0 t. E to the j 1 omega 0 t. E to the j 2 omega 0 t. E to the j 3 omega 0 t. If I use the infinite group, all of them from minus infinity to infinity, then yes, I can represent any signal within a period T0, and consequently within the other instances of T0, of TO. So this is the Fourier basis. The vectors, the signals, e to the j and omega 0 t. For instance, here, if I have a period of 2, then my frequency FO in hertz will be 1 over 2, and my frequency omega 0 will be 2 pi times this, so it will be pi, right? So if a signal has a period 2, and it is periodic, with a period 2, all I need to represent it is the set of signals e to the j n pi, which is omega 0 t. Then I will find a combination. I must find a combination of these signals, of these vectors, e to the j n omega 0 t. Each of them will have an amplitude and phase, dn, which is a complex number, which will give amplitude and phase. I sum all of them from minus infinity to infinity, and this will be x of t. This will work for the first period and for any period. So this is what we call a Fourier series. Fourier series. This is a Fourier series decomposition, or a Fourier series representation of a periodic signal x of t. Now, how to find the values for dn? When you have an orthogonal basis, you have there a vector v, which is the result of some coefficients multiplying the vectors of this basis. How can you find what coefficient is this, for instance, the first one? You do the inner product between this and the first vector. If this is orthonormal, if it's just orthogonal and not normal, then you have to divide by the norm of this. So it's inner product who's the coefficient multiplying this guy? Inner product with this and this, divide by the norm of this. Who's the coefficient multiplying this guy, the second coefficient? Inner product between them, divide by the norm. So it's exactly the same with continuous periodic signals, with this vector in this vector space. dn will be the result of the inner product. Now we are in a continuous space, so we do not do a sum, we do an integral. So it's the inner product, which is the pointwise multiplication of x of t by e to the j n omega 0 t. So I'm looking for the nth coefficient. So e to the j n omega 0 t. There's one detail here. Inner product between complex valued vectors. I have to do the complex conjugate of one of them. So let's do the complex conjugate of this one. This is why a minus appears here. So dt, this is our independent variable. We have to do this inner product along a full period. A full period, it can be from 0 to t0, it can be from 0.1 to t0 plus 0.1, it can be anything as long as it encompasses a full period. Because if I shift the interval here, I lose something here, but I gain exactly the same thing here. So it doesn't matter. It doesn't really matter where I'm choosing this whole period. And then this is not always an orthonormal basis. It can be just orthogonal, right? It depends on the size of the period. If the period is 1, then it's orthonormal. If the period is anything else, we have to divide by the norm of this guy. What's the norm of this guy? Let's write norm here. The norm would be e to the j anything. The norm across one period, t0, it's integral from 0 to t0, for instance, e to the j something dt. Absolute value. Squared, square root. Okay, now this is the norm. What's the absolute value of e to the j something? 1. So it's just 1 from 0 to t0. So it's this will give us a square with basis t0, height 1. So the norm will be t0 of this vector in my basis. So what I have to do here is just divide by t0. And here I have the inner product. Inner product between each element of the basis and the signal within one period. This will give me dn. Then I plug dn here, and I have a Fourier series representation of my periodic signal. Canonical basis. Is there a canonical basis for periodic signals? Periodic continuous signals? canonical basis, I put this there just for the sake of curiosity. We learned how to represent a signal in terms of unit impulses in the online class, right? A signal can be represented as minus infinity to infinity, x of tau, delta of t minus tau d tau. What this integral is saying is that I can represent this as a unit impulse, unit impulse, unit impulse, unit impulse times 0, times 0, times 0, times 0, times 0, times 1, times 1, times 1, times 1, with infinitesimal intervals between them. Each of them, the 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1 is here, it's coded here. This is the delay. Then the delay is here. So this is, therefore, a canonical basis. This is the basis where I have the delta of t, Dirac delta of t, Dirac delta of t minus something small, Dirac delta of t minus something small times 2 times 3, and then I get continuous canonical basis. But just for the sake of curiosity. We have the canonical basis, and now we're getting introduced to the Fourier basis, which works just the same. Well, we knew from this script that they're orthogonal. Then what we just did is this. We did the inner product. The inner product will give us 0 if m and n are different, and the inner product between two vectors of my basis, right? Between two of these guys. Otherwise, it will be T0, not always orthonormal. So this is why the T0 is present here. And then finally, we get to the definition of the Fourier series. So we can start to complete our table. I left it here in another tab. So our first actor is the Fourier series. I think we should use Times New Roman here. The Fourier series, the acronym can be FS. It can also be continuous time Fourier series, FS or CTFS. Those are the acronyms you will find. Synthesis equation. Let's use this horrible tool, which is the Google Docs equation editor. Insert equation. So synthesis, when you want to synthesize the signal from the basis vectors, which of these two equations do I have to use? The upper one or the bottom one? The upper one or the lower one?
Repeat the question.
Now we will talk about synthesis. I'm synthesizing a signal from a basis. Which one? The first one, right? I'm synthesizing from the core elements, from the atoms. Yes, this is also called an atom in the inverse problems literature. The elements of a basis are are also called atoms. With TH or just T? Atomic bomb, atomic, right? Atoms. Okay, x of t is the result of the sum from k. Is it k? No, it's n. N from minus infinity to infinity dn times e to the j omega, no, to the jn omega 0 omega 0 t. This is the synthesis equation. What about the analysis equation? In chemistry, analysis means breaking something into atoms, for instance, into smaller parts. So in the analysis, I find who are the values, dn. So it's just the Fourier integral. Insert equation. dn equals 1 over t0 the integral across a full period, t0, of the signal and the exponential with the nth harmonic, e to the minus, because of the complex conjugate, j n omega 0 t. Time domain. What are the characteristics of the signal in the time domain? For instance, we're talking about continuous or discrete signals. Continuous. What else? Periodic. We're talking about continuous periodic signals. Frequency domain. Okay, we will come back here. First, let's do 2 examples. This is a square wave from a video I have on YouTube. It's in Portuguese. I have a video about the Fourier series. And this is a triangle wave from Lathi's book. So for this one, we can derive a closed form expression for the coefficients dn. Let's do it. This signal, I'm coming back to the board. We can erase that. So let's draw the signal here. There's this, 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 and then this, this is a periodic f of t. The value here is 1. I have the link here. Let's click. And then after the ads, we'll see it. Yes, that's it. Okay, so I want to compute the values of the n for this signal. But first, what's the period for this signal? Sorry? How much? 0.1. Then the frequency in hertz will be the inverse, will be 10 hertz. Omega 0 will be 2 pi times this. So 20 pi radians per second. 20 pi radians per second. We can compute D0. And then this guy will have 0 values for even numbers. So we can compute, except for D0. We can compute D0, then D1, and then we can try to find a closed form which will give D for any value of n. So omega 0 is 20 pi. That means this signal might be represented as the sum minus infinity to infinity dn e to the jn omega 0 is 20 pi t. So if I have all the exponentials with frequencies being integer multiples of 20 pi, including 0, then I might be able to create exactly this signal. I just need to find these values. We can try to find D0. So dn, the expression is 1 over T0, the integral across T0, x of t, e to the minus jn omega 0 t dt. Let's try to find D0. So T0 is 0.1. Then I have this integral. We can integrate across one full period. Where do we want to start? I will suggest that we start here and we finish here, because then we will have a symmetric integral. Things might work out more properly. So we can integrate from minus. Actually, we have to integrate from minus 0.05 to plus 0.05. But in this interval, I'm multiplying by 0, and here just 1. So if x of t is 1 in this interval and 0 elsewhere, I can just go from minus 20.5 up to plus 0.25 of e to the minus j, n will be 0, 0, e to the 0. dt. E to the 0 is 1, right? So I have 10 here, multiplying the integral of 1 is the integral of 1 will be, what's that?
It's t, the integral.
T.
It is t.
It's t. So, yes, plus a constant, but here we have the limits. T ranging from minus this to this. So 10, this will be this minus this. So it will be actually 2 times this, which will be 0.05. It is, in the end, we have 0.5 as the coefficient for 0. Did we get that right? Yes, it's 0.5. 0.5. We don't have to compute the other ones. Let's just go to the general formula. In this case, not all cases. In this case, we can find a closed form solution for dn. Let's do this. It's an interesting exercise because we're going to do it several times in this course, because this problem will appear again and again. Can I erase this? So let's try to find general formula for dn. It's easy. 1, this is 10, 1 over t0 is 10. Here we can, let's keep it symmetric. Let's go from minus 0.5 to plus 0.05. X of t x of t e to the minus jn 20 pi t dt. Okay, now I'll do something very similar to what I've done before. If I'm integrating here, multiplying by this, I can neglect this guy from the equation and put 25 here, right? 25. Then with this integral, this is multiplying some exponential. I'm just integrating the exponential within this interval. So now the integral is not just 1. What do I get if I integrate an exponential like this? I get the same, and I have to divide the whole thing by minus jn 20 pi, right? Which is the argument that multiplies t. Minus jn 20 pi. Now the same exponential. And now this goes from this to this. And we ran out of space. We can continue here. Ten per 20, I have just 2 down here. So 1 over minus j. Yes, 1 over minus j and 2 pi. And then e to the minus j n 20 pi. What did I miss here? The t, right? The t. Here t will be this. E to the minus j n 20 pi. T will be 0.025. What is 0.025? It's 1 over 4 is 0.25.
1 over
40. 1 over 40. So we can do this. 20 over 40. The t will be the over 40. Minus. Now I substitute this here. E to the plus j and 20 over 40 is half. 0.5. This is also 0.5. 0.5 pi. T is not present here. Okay, it shouldn't be because we're integrating over t. Then we have this minus sign here, so we can swap the signs. So 1 over j and 2 pi. We put this before. E to the j n 0.5 pi minus e to the minus j n 0.5 pi. Do you know this from somewhere?
Sine or cosine.
That's a sign. When I have minus, it's a sign. The sign of x can be decomposed as 2j e to the jx minus e to the minus jx. So this is 2j. So my x here is n.5 pi. So the 2j is here. The 2j is here. So I have 1 over pi sine 1 over pi times n. 1 over pi times n.
You have to include the half. The x is n and
Well, this is the sign.
Yes.
1 over 2j, this is the sign. The rest is multiplying the sign. So 1 over NPy is multiplying the sign. Sine of n 0.5 pi is this correct? The video has the answer? Ah, yes, it's in the screen. Ah, okay. Thank you. Okay, we got the general formulation for our coefficients Tn. Do not confuse this sign with the sign which is part of the exponential. It's just a coincidence that we're analyzing a function whose coefficients are defined by a sign. Notice that this is not a sign in the time domain. It's just dictating how the coefficients behave. So let's go to the code. I did it previously, so we don't waste too much time. I did for both cases, so we are with square, with the square. I just defined the final t for the graphic representation, the sampling period, because I have to draw it in a plot. Then our omega 0 is 20 pi. My maximum n, I will compute n up to 1,000. Okay, from minus 1,000 to 1,000. Then the values of d, this is the equation 1 over pi, the sine of half n pi. For n equal to 0, this would give us 0 divided by 0. And 0 divided by 0 is an indefinite form, right? But it's an indefinite form with a well-behaved limit, which is 1. So for n equal to 0, we will have for n equal to 0, we will have 1 over pi, the sine of n 0.5 pi divided by n. So this n pi can go here. The sine of x over x is has the limit 1. So I need, what do I need here? I need 0.5. So 0.5, if I have 0.5 here, I have to put 0.5 here as well. And this limit is 1, so it's 0.5. So for d0, I'm just avoiding 0 divided by 0, so it's hard-coded here. Then I create a vector of time. Notice that the sampling frequency here doesn't matter because I am computing dn and it's not in time domain. So this is just for the graphic representation. So just for the plot. The signal is coded here. And here there's no sampling involved. So I create my time vector. This is just some experimentation I was doing. I can explain this when we study aliasing. Then here I do the summing of the Fourier representation, this sum. So x of t will be d0 times 1, the constant 1, because d0 is the coefficient that multiplies e to the 0, which is 1. And the other ones are dn times the complex exponential. And I'm computing the values of d only for non-negative values. Then inside the summation, I sum the negative dn and the positive dn. And their complex conjugates. We will come to this property in a few minutes. This property. Dn for a negative n is the complex conjugate of the positive dn. If the signal is real, and our signal is real, so I don't have to compute it twice. So I do this for n1, n minus 1, n2, n minus 2. So I do it from minus 1,000 to 1,000. And the result is here. I'm just plotting the function. Notice that I didn't provide the values of the function for each instant of time. All I provided were the coefficients. Actually, what I provided for the code was this, the general formula to compute the coefficients. Then I computed 2,000 coefficients, and I summed all the exponentials, and I got this, which is the signal we're trying to represent with the Fourier series. And then we go to what we call a spectrum. Let's just plot the coefficients. Not 1,000, now I'm plotting from minus 20 to 20. Okay, this is it. Actually, these coefficients for this function are purely real, so we don't need to divide the graph in magnitude and phase. We can plot n. What's n spec? The difference. Why did I created this variable and I'm not using the actual n? Yes, because I have only positive values for n. Now I want to plot the negative values of n too, so I created this n spec. And spec, which is the values of dn. And we go from minus 20 to 20 here too. So this is the function. This is what that gives me as dn. Here is n varying from minus 20 to 20. And those are the values of dn. Here's the half for n equal to 0. This is the value for D1. D2 is 0. D3 is something negative. D4 is 0. D5, D6, D7. And since sometimes the coefficients will be complex, I have to divide the graph into magnitude and phase. Let's put the labels here. Stem label equal to magnitude, and then plt dot legend, and here the same label. Actually, we should do this. Absolute value of dn. And the R.
For the string, don't you have to use R? You can use just like this.
Yes.
Anyway,
An or.
R, the letter R.
The letter R. Ah, yes. No, Python 3 is becoming more and more foolproof. So maybe this.
Yeah, I thought you needed to put this.
I'm not sure. Maybe I should.
No, I don't think so. If you said that expected for.
Here, absolute value, angle. This is what we call a spectrum. Why is the angle sometimes 0 and sometimes 3 point something? This is pi, right? When a number has, a complex number has angle pi, exactly pi, it's real, right? Real and negative. So here all non-negative coefficients are mirrored and represented as positive, and the negative sign is coded here as an angle. And this is what we call a spectrum. I plot the coefficients of the Fourier representation as magnitude and phase as a function of n, and this is a spectrum. As a function of n is interesting, but I prefer to plot as a function of frequency, because each of these guys is the amplitude, and each of these guys is the phase of an exponential with a given frequency. The frequency is n times omega 0. So I prefer, if we keep it like this, we can do plt dot x label n, and same here. But I prefer, here's the n, here it's hidden. I prefer to plot not the value of n, but the value of n times omega 0. And then this is angular frequency, omega, which is measured in radians per second. Yes, it's radians per second. Times omega 0. It's for the escape. then we shouldn't go from minus 20 to 20, right? Then we should go to minus 20 to, from minus 20 omega 0 to 20 omega 0, here. Now we have frequency. Now this is a spectrum. This is how much each angular frequency participates in the composition of this signal, this time domain signal. We can also multiply this by 2 pi, and we will have the frequency in hertz. Sorry, not multiply. Divide. I can divide this by 2 pi and have the frequency in hertz. Let's do this. Omega 0 divided by 2 times n p dot pi here, here. Now I have f in hertz okay. This is also a spectrum.
Your window, if your square window increases the number of sample points, you start to get more frequencies.
Sorry?
If you acquire your signal in a longer span, you also show more frequencies.
If the period is larger, then the frequency, the fundamental frequency will be shorter. Then I will have more elements here. We will see that in a few minutes. Here. We'll get to that. So we have a spectrum. What can we say about the spectrum? Frequency domain. Frequency domain representation is the spectrum. Is it continuous? No. Do you see a continuous signal here? It's a function of n, so it's discrete. So one relevant fact that you should take for life: the spectrum of a discrete signal, the spectrum of a periodic signal is discrete. Is it periodic? No. Aperiodic. Are there periodic spectra? Yes, there are. We will see them soon.